Very good morning and welcome to the lecture series session on EC402 Nanoelectronics. Dear students, today we are going to discuss about the Kronig-Penny model of a superlattice and what is Kronig-Penny model, how it is depicted, and what are all the important features of superlattice, and what is meant by swan folding. Why this swan folding is taken place in superlattices, all these things as per the Kronig-Penny model we will discuss today here. The fundamental nature of insulators, conductors and semiconductors can be functionally explained with the help of band theory. As we know that the conductors, insulators and semiconductors which are explained with the help of band theory. The recent development in semiconductor physics, the semiconductor structures are also analyzed using the concept of band theory. Kronig-Penny established a model for a solid in which the periodic potential seen by the electrons was precisely that of the square quantum potential. And this square quantum potential well type is called superlattice potential. So, superlattices are actually multiple quantum wells, which are essentially multiple quantum wells. So, Kronig-Penny has explained a model in which the periodic potential seen by the electrons was precisely that of a square quantum well type. And that particular quantum well is a superlattice potential. For that quantum well potential is essentially a superlattice potential. This periodic one-dimensional potential is characterized by the following parameters. What are those parameters? The first one is the well thickness A. Then second one is the barrier thickness B. Then the barrier height B0. That is the barrier potential height. The spatial periodicity of the potential D is equal to A plus B. So all these parameters you should remember. The well thickness A, barrier thickness B, the barrier height, that is potential height, that is V0, and spatial periodicity of the potential D is equal to A plus B. The scheme of periodic potential of superlattice is shown here now. So let us consider the superlattice. So this is actually the superlattice in which we are considering a particular quantum well here. That is considered to be a square quantum well with a quantum well with a width of the well to be equal to A, and also the thickness of the barrier to be equal to B. So this is A, well width is A, barrier width is B. So the spatial periodicity is the barrier width plus well width, that is D is equal to A plus B. Okay. Now let us consider, if you take a reference well which is to be equal to, let us consider, so actually the well thickness is A. Let us consider this as 0, 0 to A, and here this is the barrier thickness 0 to minus B. Though the thickness is B, that is, we consider the periodicity D is equal to A plus B between these 2 points. So minus B, 0, A. So this is the height of the well potential, that is V0, barrier height V0. Okay. So this is the scheme of the periodic potential with the spatial periodicity D is equal to A plus B. Now with reference to this particular model, the Kronig-Penny has developed equations, wave equations, to define the well potential, the energy, and the electron wave motion. From the periodic potential scheme, Kronig-Penny model yields the following results related to the structure of the bands, the forbidden zones, size of the gaps, etc. So actually Kronig-Penny model essentially gives us the information regarding structure of the bands, how the band structure is, then the forbidden zones, what are all the energy forbidden zones, then the size of the gaps. So different size of the energy gaps, that also we get. So all this information we get from the Kronig-Penny model. So figure shows the periodic special potential with special periodicity d is equal to a plus b, well thickness and all those things. So we have already discussed. So now we can write down the potential Vz to be equal to V0 for minus b, Z less than 0. So minus b, Z less than 0, Vz is equal to V0. Just refer here. So minus b, Z less than 0, minus b less than Z less than 0 means there is the barrier height, that is V0, isn't it? The potential is V0 here. So that is less than V0, that is potential V0 here. Then what about 0 less than Z less than A? So for 0 less than Z less than A, Vz is equal to 0. For 0 less than Z less than A means that is the potential well. The potential, of course, what is the that height of potential? That is 0. That is in the well region, the potential is 0. The barrier region, the potential barrier is V0, right? So now the Schrodinger equation representing the wave functions for the electron wave motion could be written as d square phi 1 by dz square plus 2m e minus p by h cut square phi 1 is equal to 0 for 0 less than z less than a. So for a region 0 less than z less than a, this is the wave equation, that is d square phi 1 minus dz square plus 2m e minus v, because where e is the uh, is 2m e minus p phi 1 psi 1 not phi 1 psi 1 divided by h cut square. So that is equal to equated to 0. So that is the wave equation, that is the Schrodinger equation for wave function, and this can be written like this: d square psi divided by dz square plus 2me psi 1 by h cut square is equal to 0, because here voltage V in between the section minus b z less than 0, the voltage V is equal to volt, that is this one, 0 less than z less than a, the voltage Vz is equal to 0, that we have seen. So that is why this V is equal to 0. So since V is equal to 0, this equation becomes 2me psi 1 by h cut square plus 2 d square psi 1 by dz square is equal to 0 for 0 less than z less than a. So if you just um, rearranging the equation in the form like this: d square psi 1 by dz square plus k0 square, a constant k0 square psi 1 is equal to 0 for 0 less than z less than a, for 0 less than z less than, because in the well region V is equal to 0, that is why this equation becomes like this. Okay, where k0 square is equal to 2me by h cut square. Okay, now the solution for the equation is given as psi 1 z is equal to a e ik0 z plus e ik0 z. This we can find out. Of course, this differential equation could be solved. Schrodinger equation, this differential equation could be solved, and you will be getting an equation like this, where k0 square is equal to me by h cut square. And due to tunneling, the wave function extends inside the energy barrier. So when due to the tunneling effect, what happens? The wave function extends. That's what we have seen. The wave function extends inside the energy barrier of height V0 and thickness b. The Schrodinger equation for barrier region, that is minus b less than z less than 0, that is the barrier region. And in that barrier region, of course, V0 is higher than E. In the barrier region, energy is small and V0 is high. That is why d square psi 2 divided by dz square, because on the barrier region, the wave function is psi 2, that is d square psi 2 by dz square minus 2m V0 minus E by h cut square psi 2 is equal to 0. This can be reduced like this: d square z psi 2 by dz square minus q square psi 2 is equal to 0 for region minus b less than z less than 0, and where q square is equal to m into v0 minus e divided by h cut square. Okay, where h cut square is the reduced Max Planck constant that you might have already learned. Of course, the same thing is written here again, and we get the solution for this equation to be equal to xi2z is equal to ceqz plus de minus qz. Okay, these are also the equation readily available by solving this equation. Okay, and here you can see in the first case you can see a, that is a, first case the equation solution is y1z is equal to aeik0z plus be minus ik0z. And in the case of second equation xi2, that the wave function, second wave function xi2z is equal to eqz plus de minus qz. That is equation 6. So equation 4, 5, 6 we have to mark it. And then ABC, what are these ABC? The A, B, C and D are the constants which represent the amplitude of the wave function. Amplitude of the wave function. Okay. Now, from the condition that both wave functions and their derivatives are continuous at z is equal to 0 and z is equal to a. And in this particular model, the wave functions are and its derivatives. The wave functions and their derivatives are continuous at z is equal to 0 and z is equal to a. So, under this condition, we can say that xi1 z is equal to xi2 z. That is equation 7. And again, what is xi1 z is equal to xi2 z? That is the wave functions are continuous in nature, and its derivatives also are also continuous at z is equal to 0 and z is equal to a. That is d xi1 divided by dz is equal to d xi2 divided by dz. That is z is equal to 0. And similarly, xi1 z is equal to a is equal to xi2 z is equal to minus b, where we can consider instead of a, we can rearrange this equation by taking z is equal to minus b. In that case, dxi1 by dz, when z is equal to a is equal to dxi2 by dz, then z is equal to minus b. Okay, so applying these conditions 7 and 8 to equation 2 and 6. Equation 2 and 6 we have already seen. 7 and 8 also we have seen equation 2 and 6. Equation 2 is this one. Xi1 is equal to aeik0 z plus be minus ik0 z. Okay, so when we apply this equation z 7 and 8 to equation 2 and 6, we get the relationship a plus b is equal to c plus d. Of course, these are all mathematical manipulations that you should understand. That's all. And whenever it is asked to explain the Kronig-Penny model, you have to write down the equations and its solutions directly. So that equations and solutions you have to write down. Then you can manipulate equations by mathematical methods. So here dxi1 by dz is ik0 a e raised to minus ik0 z minus b e raised to ik0 z. Similarly, dxi2 minus dz is q into ceqz minus deqz. And in this particular case, you can see ik0 a minus b is equal to q into c minus d. So this is considered the equation number 12. Now, how can you find out the values of this equation? How can you solve this equation? And in order to find out the solution for this equation, we need to have another two more equations. And that is obtained with the help of applying the boundary conditions using Bloch's theorem. What is going to be Bloch's theorem? Bloch's theorem states that the solution of Schrodinger equation for a particle in a periodic potential is the product of a function with a period of the lattice and the plane wave equation. You have to understand this Bloch's theorem. What is Bloch's theorem? Bloch's theorem states that the solution of Schrodinger equation for a particle in a periodic potential is the product of a function with a period of lattice and the plane wave equation. It means that the periodicity d is equal to a plus b, Applying Bloch's theorem for the wave equation, what happens? Why k? Because here the vector, when we apply the special sphericity, of course using Gauss theorem, we will form an equation with the k vector. The wave function is actually with this k vector, that is yk z a plus b is equal to yk z e raised to ik a plus b, or yk z, wave function yk z is equal to yk z plus a plus b e raised to minus ik a plus b. So that is Gauss theorem. Okay, so if you apply this Gauss theorem and form the equation, this equation, that is psi k z is equal to yk z plus a plus b e raised to minus ik a plus b, because the spatial periodicity of the periodic potential is d is equal to a plus b. So a plus b we have written directly here. So according to Gauss theorem, again if we apply z is equal to minus b, we can relate the wave functions of two different locations. That is different locations by means, that is z is equal to minus b and z is equal to a, like that. Okay. So according to Gauss theorem, again at z is equal to minus b, we can relate the wave equation at two different locations by, what are those equations? Phi 2 minus b is equal to phi 1 a e raised to minus ik a plus b, putting z is equal to minus b and z is equal to a in equation 6 and equation 2 respectively. Then what happens? We get this solution for this equation to be equal to CE minus QB plus DE cube, and that is equal to AE IK0A plus BE IK0A into e raised to minus IK0A. Or we can say that d psi 2 dz, where z is equal to minus b is equal to d psi 1 dz e raised to minus ik a plus b, where z is equal to a. So we can relate the conditions using Gauss theorem, using this particular two different locations, and applying the Gauss theorem to the equations, so that we will be getting the solution equal to this particular 14th equation, that is CE minus C e raised to minus qb plus d e raised to qb is equal to a into e raised to minus ik0a plus b into e raised to minus ik0a into e raised to minus ik0a plus b. So this particular equations can be written, and that is equal to 40, equation number 40. Then applying equation 13 to equation 10 gives, what is this? That gives q c e raised to minus qb plus d qde qb is equal to a e raised to ik0a minus b e raised to minus ik0a into ik0 e raised to ik0a plus b. So this is the 15th equation. Here the k is the wave vector corresponding to the wave function. Actually here we are actually using the k vector to represent the wave equation corresponding to the wave equation, and a, b, c and d are the amplitude of the wave function. So equation 11, 12, 14 and 15 can be written in matrix form like this. So this is the matrix form of the equation. What are those equations? Equation 11, 12, 14 and 15. That is written in matrix form. That is, so this is the matrix. In this matrix, coefficient into a, b, c, d is equal to 0. That will give the equation, 4 equations. The 4 equations 11, 12, 14, 15 for amplitudes a, b, c and d have a solution. This equation have a solution, that is this coefficients into a, b, c, d has a solution if and only if the determinant of this coefficients is equal to 0. That is why the determinant of this particular matrix is given here, that is equal to 0. If you expand this determinant and equate it to 0, if that particular determinant, value of the determinant is equal to 0, then of course we can have a solution for the 4 equations. On solving the above equation successively, then we will be getting an expression as q square minus k0 square divided by 2k cube 0 sin k0 a sin h cube b plus cos k0 a cos h cube is equal to cos k a plus b. So here there is a hyperbolic function and this is cosine function. The following conditions should be satisfied for valid wave function of the electrons propagating through the upper lattice. What are all the conditions? The wave vector propagating electron is k is equal to 2 pi by lambda. The wave vector propagating electron is k is equal to 2 pi by lambda, where lambda is the wavelength. Okay, wavelength, the de Broglie wavelength in the case of systems, structures, nanostructures. Okay, 2 pi by lambda, where k is the wave vector, that is given by 2 pi by lambda. Now suppose the barrier thickness B is equal to 0. Barrier is very small thickness of filling. So let us consider that small thickness B almost equal to 0. That is negligible thickness. In that case, the voltage V0 remains finite. Then sin h qb tends to qb and cos h qb tends to 1. Sin h qb tends to qb and cos h qb tends to 1. Then equation 16 then becomes q square minus k square into qb divided by 2k q0 is equal to into sin k0a, because sin h b becomes qb, that is shown here. Sin k0a, that is sin k0a plus cos k0a, cos k0a into cos h qb, cos h qb becomes 1, so it becomes cos k0a is equal to cos k a plus b, or k cos k b is equal to 0, so it's cos k a. So this equation 16 becomes like this. Okay, and we can see that q square minus k0 square is almost equal to 2mv square, 2mv0, that is 2mv0, that is the potential barrier, where the cut square approximately, because E is far less than V0 in the barrier region. And if that is the case, equation 17 becomes 2mv0 by h cut square into qb by 2k0 2k0q sin k0a cos ka is equal to cos ka. So simplifying this equation, we will be getting sin f sin k0a divided by k0a plus cos k0a is equal to cos a, where f is equal to mv0 ab divided by h square. Okay, so now if you consider the quantities k0 and k, which are variables, and the RHS of equation 18 can take a value, that is RHS of this equation 18 can take a value, this is equation 18, which can take a value as cos ka, cosine function can take a value between -1 and +1, isn't it? -1 and cos 180 is equal to -1, cos 0 is equal to +1, isn't it? So the value of this function for this equation, the left hand side is equal to cos k, so it has got a value between -1 and 1, that is shown here. It means that the values of k and hence the energy of propagating electron through the superlattice is restricted. So since the value of energy can be restricted between 1 and -1, isn't it? So this means that the energy propagating electron through the, or energy of the propagating electron through the superlattice is restricted between these values, -1 and +1. So k0 square is equal to me by h square square, or E is equal to energy E is equal to h cut square k0 square divided by 2m. So we can plot the allowed energy bands, and this is actually the allowed energy band, that is the electron wave motion, that is the wave motion here. So we take the maximum value of that amplitude of f by k0a sin k0a plus cos k0a. So in this particular uh, band diagram, this is actually the energy level, the band diagram, which can take a value between the allowed energy level can take a value between 4 plus 1 and minus 1. That is shown here. And when if you consider this wave, energy wave function, you can see there are that firm lines here. This is firm line, but there is a gap here. Then there is again firm line. There is a gap. So this firm line represents the allowed energy band. Firm line, which represents the allowed energy band, and this is actually a gap. This is gap. So the allowed values of energy corresponds to the part of curve lies between plus 1 and minus 1. The bold bars, that is this one, the bold bars, this one. This bold bars give the possible value of Ka. This gives the possible value of Ka, and hence the possible value of energy. It is important to note that the forbidden bands of energy occur for energies for which mod K is greater than 1. The forbidden band of energy occur for energies for which the Ka is more than 1. So more than 1, if the value of energy is more than 1, that is the forbidden band of energy. That is forbidden band. So there are forbidden bands of energy that occurs for mod K is greater than 1. And for the allowed energy bands, which always lies between plus 1 and then minus 1, shown here. Okay. So this is the bold line which represents the allowed bands. This is allowed band. This is allowed band. This is allowed band. This is also allowed band. This is a gap. This is also, so here the energy band is not continuous, there is gap. So this is K0 A axis and this is energy axis, that x by K0 A and K0 x the solution of the equation. Now for each value of K, we find a horizontal line for cos Ka. The meeting points of the curve with this line gives the possible energy values of the electron propagated through the superlattice. That I told you, this is the allowed band. From here, if you draw a line perpendicular to the wave and which cuts here the positive side. So if there are different values of K between minus 1 and 1 for the energy values, you can take any value of K0 J in between. So that is the K0 value, so that you will be getting different points here like this, so that different energy levels can be, or energy that is allowed energy bands could be identified like this between minus 1 and plus 1. Okay. For a given value of K, large number of energy values are possible. Repeating the procedure for various values of K, we get energy E. Thus, we can plot Ek graph. Once we know the energy for each value of K, we can plot the Ek graph. And the Ek graph of electron which can propagate through the superlattice, which is shown in the diagram here. So this is the Ek graph. Okay, this is the Ek graph. So here you can see this is the bulk 3D material where the energy band, that is the energy band diagram. This is actually the parabolic potential. This is parabolic potential for square quantum wells. So for square quantum wells, this is the parabolic potential. But in the case of superlattice, this parabolic potential has got the edges folded like this. Here, if you consider this wave vector K is equal to 0 and K is equal to pi by d on one positive and pi by d negative. So in between this one you can have the energy band, allowed energy band like this. Here between minus pi by d and minus 2 pi by d, this is the allowed energy band. So there is a gap. Here also there is an allowed energy band. There is a gap. Similarly from here there is a gap. Likewise, the band, energy band is folded on these zones. And what these zones are called, we will just see now. Features. The solution exists for a certain range of cases. Therefore, the motion of the electrons in a superlattice is characterized by the band of allowed energy separated by a forbidden region. The width of the allowed band increases with K0. The width of the allowed band increases. That is what we have seen here. The width of the band. This is the width of the band which increases with K0. The quantity F is a measure of the strength of the potential barrier. Actually, this F is a measure of the strength of potential barrier. If F is large, V0, B is large, and allowed bands are very small. So now we have seen this one. This actually the parabolic potentials are now folded between the regions we have seen here, and these zones where this energy bands are folded are called Brillouin zones. So likewise, from k is equal to 0 to k is equal to pi by d, this is the first Brillouin zone. Similarly, k is equal to 0 to k is equal to minus pi by d is the, or that is pi by d to the minus pi by d to plus pi by d to plus pi by d, minus pi by d to plus pi by d, the first Brillouin zone is there. From plus pi by d to plus 2 pi by d, again we have a Brillouin zone. Similarly, minus pi by d to minus 2 pi by d, there is a Brillouin zone. So each Brillouin zone, the energy band is folded as shown here. This is a folded energy band. This is the actual parabolic square quantum potential. That is the square potential. That is the energy, the parabolic quantum potential. Okay. Here, this is folded in between the regions, what is called the Brillouin zones. And this particular feature is called the zone folding. The zone folding. So in superlattices, this phenomena of zone folding is quite common. The energy is not continuous. There are band gaps. There are energy band gaps like this. Here like this. Here it is like this. So where the energy is zero, there is no energy. There is a gap of energy. So likewise, if you consider this, the Brillouin zones between minus pi by d to pi by d, see this is the extended energy band diagram in the first Brillouin zone. So it is shown like this. See, this is this one, isn't it? So similarly, this is shown here. Similarly, in the first Brillouin zone, if you consider this band, so it comes like this, goes like this, then it increases like this and goes like this, comes like this, and reaches here like this. That is why it is shown here like this. Similarly, for first Brillouin zone of this particular band folding, again this comes like this, goes like this, and again comes like this, and goes like this, again comes like. So it is like this. So this is the energy band. So wave vector k, energy Ek. Okay, in the first Brillouin zone. So this is actually the extended band diagram for the wave vector k. Okay. Now, what is meant by Brillouin zone? The Brillouin zone is a representation of permitted values of k of electrons in a periodic lattice. That is actually this Brillouin zone is a representation of permitted values of K of electrons in a periodic lattice. Now let us consider the possible values of K from equation 18. We see that the discontinuity in energy when cos K is equal to plus or minus 1 or K is equal to, if cos K is equal to plus or minus 1 means K is equal to plus or minus n pi, or K is equal to plus or minus n pi by A, where n is equal to 1, 2, 3, right? So the possible values of K in allowed bands, which are called Brillouin zones. The possible value of K in the allowed bands is what is called the Brillouin zone. The first Brillouin zone is from minus pi by A to pi by A. So in the case of superlattices, this minus pi by D to plus pi by D. The second Brillouin zone is from minus pi by A to 2 pi by A, then and minus pi by A to minus 2 pi by A. The most important feature of Kronig-Penny model is the prediction of band structure in superlattice. Actually, that is the important feature with Kronig-Penny model. We can predict the band structure and we can create a new material by predicting its band structure, right? So what is the effect of zone folding? A superlattice consists of materials with lattice constants A and B, which has a spatial sphericity of A plus B. So superlattice has a lattice constant of A and B. Therefore, the first Brillouin zone edge of such a superlattice is given by 2 pi by A plus B, that is 2 pi by D, indicating that a large unit cell results in a smaller Brillouin zone. In other words, Brillouin zones of bulk materials 2 pi by A and 2 pi by B are folded into a smaller zone with 2 pi by A plus B in a superlattice. So for bulk materials 2 pi by A, 2 pi by B are mentioned, but when it is a smaller zone for superlattice, it is represented as 2 pi divided by A plus B in a superlattice. As a result, many mini bands are formed in superlattice. Actually, due to this superlattice nature, many mini bands and gaps are formed. This feature of mini band formation in superlattice is called zone folding effect. Actually, zone folding effect occurs in the Brillouin zones. So here the figure shows mini band formation for smaller thickness, barrier thickness for superlattice, and no bands are formed for wells with large barrier thickness. Here, this is for large barrier thickness. That is, this is well with large barrier thickness. There is no band formed. There is no mini band formed. But when the well thickness with the barrier is very small, see, this is well with small barrier. Here it is large barrier. So here many bands are formed. So many band energy bands and band gaps are formed. So here no bands are formed in the case of figure A, and here B many bands are formed in superlattice. So this is the case of a superlattice. Okay. Now with the situation 16, assume the case that well width A is equal to B. That is, well length barrier has got the same width A is equal to B, and the effective mass of electrons is same in the well length barrier. So while electron penetrates or which actually tunnels through the barrier, the effective mass of electrons are not changing. Same electron mass, wave mass is there for the electron wave motion. For the case of gallium arsenide, aluminum gallium arsenide, and E is less than V0, equation 16 gives the value of the allowed and forbidden energy, which are represented in figure A for a lattice with a band discontinuous. So that is given as the example for a superlattice of gallium arsenide, aluminum gallium arsenide, and here in the superlattice with a band discontinuity of 0.3 electron volt. So band discontinuity, that is band, there is a gap, and that gap is actually 0.3 electron volts, and for the effective mass of electrons, Me star is equal to 0.067 M0. Okay, so this figure represents the allowed energy band and the band gap. It's a gap. So this is the allowed. So here, so at 0.3 electron volt at the edges of this one. Actually, this is the band at the edges, and there is gap between. So like this is the band. So this is the band, allowed energy band, and there is a gap here. Similarly, this is allowed energy band, and there is gap here. Similarly, this is allowed energy band, gap here. So again here there is a gap. So this energy band diagram represents the energy band diagram of a superlattice with the width of the barrier equal to the width of the well. Okay, so here it can be seen that the general features of energy wave vector, that is EK diagram. This is what is called EK diagram. Energy wave vector means energy EK, K wave vector, K. And this relationship in a superlattice within the Kronig-Penny model are very similar to the case of electrons in bulk solids if the bulk lattice constant is replaced by a larger period of superlattice. Okay, so this diagram shows an EK diagram in which the relationship of this, with regard to superlattice as per the Kronig-Penny model are very similar to that of a bulk material or bulk lattice constant, and that can be replaced by a large period of superlattice. If that is the case, we can see that for bulk material we can have the parabolic potential like this, isn't it? But in the case of superlattice with the lattice constant replaced by large period, you can see that the edges of this particular parabolic potentials are now folded like this at each Brillouin. So it's represented by 0 minus pi by d to 0 pi by d. That is the first Brillouin. So then minus 2 pi by d to 0 to 2 pi d. Second Brillouin zone like that. So this Brillouin zone, that is the first Brillouin zone is shown here, in which what is the wave diagram, that is the energy wave motion, energy wave function diagram. That is the energy band diagram for the first Brillouin zones. Energy band diagram with respect to the wave vector k. Okay, the first Brillouin zone, this is represented like this. This wave function, this wave, that energy, that is this parabolic potential shown here, that is folded at the edges, which is shown here. Okay. Now, figure B shows that the values of A larger than about 10 nanometer. The electron energies are well defined and correspond to individual quantum wells. If the well thickness or well size, the value of A is more than 10 nanometer, that in the case of a quantum well. The electron energies are well defined, that is almost nearly equal to individual quantum wells. And when the barrier width is lesser than 6 nanometer, that is smaller, that is smaller than A, that is 10 nanometer, that is 6 nanometer. If it is smaller than A is to 10 nanometer, already we have said for individual quantum wells. But if the well thickness is reduced, say about 6 nanometer, the band as well as the forbidden zone arises. So, if the well thickness is reduced less than 10 nanometer, for if it is more than 10 nanometer, the individual quantum wells will be existed, and the system, the material will behave exactly like a individual quantum wells. But if the quantum well size is less than 10 nanometers, say 6 nanometers, then the bands as well as the forbidden zone arises. Separate allowed bands of energy and forbidden zone arises. The free electron parabola therefore breaks down into several bands. What is the free electron parabola? The free electron parabola is the wave potential for a square quantum well, that is individual quantum well, isn't it? But when the barrier width is less than 6 nanometer, when the barrier width is less than 6 nanometer, then the bands will show or bands will exhibit separate energy allowed bands and forbidden zones. Or in other words, the parabolic potential well will be broken down into several bands and gaps at the edges of the Brillouin zones, where the Brillouin zones are represented as k is equal to plus or minus n pi by d, as shown in the extended decay diagram we have seen here. This is the extended decay diagram with each Brillouin zone. First Brillouin zone represented here, the second Brillouin zone here, third Brillouin zone like that. Okay. So here the first Brillouin zone, this is the decay diagram. Okay. So if the well size is larger than say some 10 nanometers, then that well will be exhibiting or that will be correspond to an individual quantum well and which will be having uh, individual quantum well parabolic potential. But when the barrier width is less than 10 nanometers, say some 6 nanometers or so, then there will be allowed energy bands as well as forbidden zones or gaps, so that the parabolic potential of the quantum well in the individual quantum well, that will be now considered to be broken into several small bands with allowed gaps, that forbidden gaps, at the edges of the Brillouin zones represented by k is equal to plus or minus n pi by d, which is shown in the extended decay diagram. The portions of the bands that can be translated into reduced zones, that is minus pi by d less than z less than or equal to plus pi by d, that is the first Brillouin zone, that is shown here. That is shown here, that is the first Brillouin zone shown here. Usually, the spatial periodicity d is far greater than a. The breadth of the bands and gaps in a superlattice are much smaller, called mini bands and mini gaps. So this formation of mini bands and mini gaps at the edges of the Brillouin zones in the band structure of the decay diagram is called the band folding procedure or zone folding. So the formation of mini bands and the band gaps occurring at the Brillouin zones is called the band folding phenomena or zone folding. And this particular phenomena is called the, or this particular feature of the superlattice is called zone folding, since it implies that the pieces of the band in the extended representation are zone folded into smaller zones with values of k smaller than 2 pi by d. The zone folding effect has important consequences in the direct or indirect character of the semiconductor structure. Actually, this zone folding effect, which can very easily control the band structure. So that in order to create a new material, a new solid with a particular band structure, it is possible. So it is this swan folding effect which has got some important consequences in the direct or indirect character of a semiconductor structure. And here, this is actually a superlattice zone folding effect in the band diagram of an indirect gap semiconductor. So here it is in the wave vector is represented here 2 pi by 2a, this is 2 pi by a 0. So this is underlying zones and this is the allowed band and gap that is shown here for a particular semiconductor material. As indicated by the dot line in the figure, the minimum of the conduction band is translated to K is equal to 0. That is shown here. The minimum of the conduction band that's shown here as dotted, that is translated to K is equal to 0. So that is shown here like this. Here it is like, okay, K is equal to 0. So what actually means it? The resulting semiconductor structure should therefore show a direct gap at K is equal to 0 of the same energy value as the indirect one. So this unfolding effect has a direct consequence in the direct or indirect character of the semiconductor structure due to this phenomena. And what does it yield really? Based on the unfolding concept, one can fabricate superlattice of gallium aluminum arsenate, that is gallium arsenate and aluminum arsenide with direct and indirect gaps respectively, which shows quasi-direct optical transmission. So based on this unfolding concept, one can fabricate a new structure in the form of a superlattice using gallium arsenide and aluminum arsenide, which show quasi-direct optical transmission. Another example is that is silicon N and germanium, that is superlattice based on SIGE heterostructure. SIGE heterostructures can also act as superlattice, which are constructed usually symmetrical N is equal to M. That is the lattice constant. Silicon N, lattice constant, germanium M. If N is equal to M, symmetrical structures of the superlattice could be arranged. The minimum of the SI conduction band close to the band edge can be brought close to K is equal to 0 by successive zone folding. So actually this zone folding concept helps us to fabricate superlattice of semiconductor materials with well-defined band structure. Or in other words, we can create the band structure of a material, new material, with controlled band structure. That is why superlattices are sometimes called artificial solids, because its band structure can be controlled by using the zone folding concept. And what are all the applications of this one? Due to small widths of the mini gaps and mini bands in superlattices, as well as the quasi-direct type of transition, superlattices find many applications in infrared optics, especially infrared photodetectors and of course infrared devices. In addition, they can show properties like 1h dark localization and Bloch oscillations that are also possible with this device. So these are all the practical applications. Mainly they are used as infrared photodetectors or infrared optics. This particular device are used. Okay. So with this we conclude the superlattice and the Kronig-Penny model of superlattice and the related theory behind superlattice. How the Kronig-Penny model explains the wave functions, the electron wave motions, and the K diagram and the zone folding concept, how it affects the direct and indirect method of band structure formation in semiconductor structure. Okay, thank you very much for hearing my session. Wish you all the very best. Thank you.